So thanks so much for that amazing introduction, Divya. It really is a pleasure to be here speaking with you today. So before I get started, just a quick poll. First of all, how many of you have heard of one new feature in the latest version of EcmaScript, EcmaScript 6? Okay, excellent, so good mix. How many of you, conversely, don't know what EcmaScript is at all? Okay, alrighty, so won't be completely redundant while I explain. So please bear with me, all your questions will be answered. So let's go ahead and get started talking about the next revision of the language. As I'm sure some of you may have heard, there is a new revision of the language that is being currently prepared and worked on by a working group in a committee. That revision is called EcmaScript 6, and it brings along some much needed syntactic conveniences and APIs to existing JavaScript code. One of the things that fascinates me most about technology is that every technology has a story behind it, and EcmaScript 6 is no exception. But like in any good story, it's not just comprised of the primary protagonists or any earth-shattering situations. In any good narrative, there are a lot of different aspects, and oftentimes it's the supporting characters or the amalgam of various individual situations that might not seem to be particularly earth-shattering on their own, but when combined, actually create a significant influence. Sorry about that. Feedback? Okay, so in this presentation, I'll not only hope to talk to you a bit about the new features in EcmaScript 6, but also tell you a bit about the story. So without further ado, let's begin. Our story begins, as these stories often do, with an up-and-coming engineer at Netscape Communications Corporation in 1995. This particular engineer is tasked with writing a client-side scripting language to complement and capitalize upon the Java craze that was occurring at the time. In 10 days, he conceives a language called Mocha, which is then changed to LiveScript and then hurriedly changed to JavaScript before shipping in the latest and greatest browser at the time, Netscape Navigator 2.0. Now, JavaScript quickly eclipsed its distant and rather confusingly named cousin and is implemented by Microsoft under the name of JScript and then integrated into its browser at the time, IE3. Shortly thereafter, Netscape submitted JavaScript to the ECMA, the European Computing Manufacturers Association, which was then distilled into the trade name of EcmaScript. The creator of JavaScript, Brendan Eich, has been known to comment more than once that the trade name of EcmaScript was never particularly well received by anyone. In fact, it sounded very much like a skin disease. But nonetheless, it was the name that was selected for the language. So this you can think of as the standardized version of JavaScript. What we colloquially refer to as JavaScript is actually one of several implementations of the EcmaScript standard. Whereas JavaScript itself, when used as a trademark, is actually owned by Oracle and licensed by Mozilla. It's the name that Mozilla uses for its specific JavaScript implementation that's present in Firefox, Thunderbird, and SeaMonkey. So it's an interesting, so JavaScript's history is not only intriguing in its syntactic development, but also the naming. From the very beginning, it needed to share a name with its distant cousin and then adopt a series of various names and implementation engines. So JavaScript and JScript were back in 1996 at the time, continued to diverge from the parent specification, and shortly thereafter, the ECMA released a second draft that was primarily targeted at bringing JavaScript, or EcmaScript rather, in line with existing international standards. But it wasn't until 1999 that the language really took off with the third edition of EcmaScript. It introduced features that today we would consider absolutely essential to programming. Things like regular expressions, additional string methods, new control statements like switch and do while, new operators like in and instance of, exception handling, tighter error semantics, and features for numeric formatting and other international changes. Now at this time, because JavaScript had experienced such a surge of popularity, the specification was built such that it would anticipate future growth with a follow-up fourth edition. It was a fantastic time to begin standardizing the language. But alas, the fourth edition was not quite meant to be. In 2005, the technical committee responsible for moving the language forward, TC39, released a draft of the EcmaScript 4 specification. And looking at it, and comparing it to the specification responsible for the third edition, it's very difficult to see any resemblance between them. The EcmaScript 4 draft inherited several features from divergent implementations like ActionScript. So interesting enough, what Adobe did with ActionScript was to start with the base of EcmaScript 3 and then extend it with additional semantics, like say static type checking, classes, packages, namespaces, and even conveniences like block scoping, generators, and REST parameters. And so you can look at ES4 as an attempt to take those syntactic additions and integrate them back upstream into the specification. But unfortunately, there was a general consensus that ES4 lacked focus and that was becoming an incredibly backward incompatible revision of the language. And normally iterating JavaScript might not have presented such a significant concern. After all, the try-catch statement was introduced in ES3 in 1999, so it took a few years before before developers could use them in every implementation successfully. But it was also in 2005 that Jesse James Garrett had coined the term AJAX, launched the AJAX revolution. Suddenly, companies and web developers were able to build complex, highly dynamic applications using a scripting language that had last been modified and had seen a significant revision in 1999. So there was great concern that the 4th edition of the specification would end up breaking the web. Now, JavaScript as a language is very unique because the barrier to entry to it is so low. Almost every browser on the planet ships with some form of JavaScript engine. And today, experimenting with it and even beginning to write your own programs have never been easier. In fact, with the multitude of dev tools that are shipping in modern browsers, all it takes to start writing and learning So in 2005, browsers had not yet become as sophisticated, but nonetheless, backward compatibility was a concern. So it was with perhaps not too much reluctance that TC39, the technical committee, decided to shelve the draft of ES4 and create an implementation called EcmaScript 5. Today, if you look on the ECMA website, you'll see a list of historical specs, but interesting enough, ES4 is nowhere to be found. That's because the specification never reached any status beyond a basic draft. Instead, TC39 regrouped and released a version of EcmaScript called EcmaScript 5 in 2009. Now, compared to the difference between ES3 and ES4, the revisions were primarily conservative. It tightened down some semantics around regular expressions, eval, and global objects. It added some new object reflection methods like object get prototype of, define properties, and even object.create. It added the array extras that Mozilla had implemented in Firefox 2 about 2-3 years earlier. It added strict mode and native JSON support, and its only syntactic extension were getters and setters. So under the hood, though, EcmaScript 5 represented a significant undertaking to revamp the internals of the language. And it's upon these successes that the next version of the language, EcmaScript 6, builds. So here we are in 2013 with a specification slated for completion before the end of the year, and we've come full circle. If EcmaScript 5 was a conservative change, ES6 is showy and flashy. There are many different features available, from class syntax to block scoping to constants to WeakMaps and other new data structures, shorter function syntaxes, private symbols, default parameters, and even some more under the hood goodies like tail call optimizations and full Unicode support for strings. Now, the important point to stress here is that despite this wealth of changes, ES6 is completely backward compatible with ES5. That means that all existing code that you've written today that runs in all engines will continue to remain valid EcmaScript 6 code. There's absolutely no need to worry about any breaking changes. Now, Mozilla has been innovating many syntactic extensions of JavaScript in the past, and their solution was to use whenever you include a new script that uses the syntactic extensions, you would specify a new content type parameter. So if you wanted to use, say, generators, which Mozilla inserted into its implementation and versioned at 1.8, you would do script type equals text JavaScript, and then with a comma, and then version equals 1.8. With EcmaScript 6, there's none of that. The syntax is purely additive. So if you're not particularly keen on any ES6 feature, or if you're worried about upgrading, there's absolutely no need for you to preoccupy yourself with backporting previous code. Your existing code will continue to just work, and if you want to take advantage of the new features, all you need to do is begin writing them. So let's go ahead and take a look at some of these latest features. Some of them, like classes and modules, have sparked a lot of discussion within the JavaScript community, to the point where I almost feel that we ignore some of the finer things. As I hinted at the beginning of the slides, it's not necessarily about the major protagonists, but rather it's about the small syntactic extensions, the secondary characters that will truly allow us to write code that is both leaner and easier to peruse. So let's have a look at some of these extensions. The very first one is block scoping, and EcmaScript 6 introduces two new keywords for accomplishing this: let, which creates a block scope variable, and const, which follows the semantics of let, but creates a read-only constant declaration. So let also introduces new semantics for blocks. Previously, blocks were advisory and primarily as a way of grouping additional code or when they were specifically required by a particular statement. But with ES6 though, that changes. Function declarations are also now supported within blocks. Previously, this was a syntax error, but implementations often disregarded this to create for some interesting, if not rather confusing behavior. So let's take a look at an existing valid EcmaScript 5 code. You can see that we have an if statement with a variable declaration in it. We're declaring the var value and assigning the number 1, 2, 3, and we're defining a function declaration get value that returns the resulting value. Now you can see that this is defined within an if statement where the condition is false. So this should never execute, right? No. What happens is if you run get value outside of that block, first of all, you'll see that it actually runs. It doesn't throw a syntax error. That function declaration was actually hoisted to the outer scope, either its containing function, if this is located within a function declaration or expression, or to the global scope. So what ends up happening is that the variable declaration got hoisted as well, but the initialization part of it that assigned it the value 1, 2, 3 occurred within the block. So as a result, when you run get value, it'll return the value undefined because the value variable has been declared, it just hasn't been initialized because it's contained within that if false block. So this is one of the most confusing semantics about the language. And with ES6, you can now use let and function declarations to work as before. You'll notice that I've made only one adjustment here, that I've changed the var keyword to a let. But now, if I try running get value outside of the if statement, it'll throw a reference error, which is in line with more what developers expect. So to recap, we have new semantics for blocks, and function declarations may now be declared within blocks. So rather than having the implementation continue to forbid them, it'll be a useful syntactic extension that's in line with what developers expect when they write code like this. So another common pattern is one that I think appears in almost every presentation about JavaScript's quirks, and that is trying to create functions within a loop. So you can see here that I have a counter variable that I start at 2, decrement it, and then dynamically assign a function. We can assume that $ is my jQuery-like library that I'd like to add DOM methods to. So I'm defining a getWidth and a getHeight method. But the problem is, because that dimension variable declaration gets hoisted to the containing block, both of those methods will end up returning the element's height, since when I set the counter, if it's 0, I want to use the offset height variable instead of offset width. So as a result, this function doesn't do what you'd expect at all, and you've just defined several functions that all return the same value. So not too useful. In ES6, the solution is to change one line in this case. I changed the var declaration from var dimension to let dimension. And suddenly everything works as expected. GetWidth will now return the width of the element, and getHeight will return the correct height. Previously, you would have to create your own closure to support this, which tripped up many developers, or you'd need to rely on edge case semantics to either use a try-catch block or a with statement. With ES6, that goes away entirely, and we finally have a syntax for doing block scope declaration. Some other interesting gotchas is that the language will make it even easier to It will make it even easier to accidentally trip over your own code. So you can only declare block scope variables within blocks rather than just as individual statements. You can't redeclare constants, and you cannot override constants with additional values. You also cannot have a variable declaration with var share the same name as one that uses a let or a const declaration. So the point is to make it, as I said earlier, to make it easier for you to write code that is rather predictable without having to worry about new quirks. And this is especially important if you're just getting started with the language and don't necessarily want to take the time to master all of its quirks and edge cases. And it does take a while. The next aspect that I would cover are shorthand object literal syntaxes. Now, the shorthand object literal syntax allows us to cut down on boilerplate. You can see here that I've declared two variables, name and occupation, and then have created an object literal that contains the name and occupation properties. But that seems very redundant, doesn't it? All I'm doing is assigning the two variables to the corresponding object literal properties of the same name. So ES6 allows me to write this in about half the number of lines. All I need to do is just initialize an object and specify just the names of the variables. And those will automatically be bound as properties that share the same name. The second syntax that I'd like to cover are method definitions. And it helps to start with an example. So you can see on this next slide that I've created a simple constructor and I'm assigning an object to its prototype, so defining additional methods on it. I'm using the ES5 getter and setter syntax, so that's not new in this revision. But look at my declaration of the speak method. You'll notice that I'm not specifying the names, you'll notice that I'm not using the colon syntax to define the speak property, and I'm not using the function keyword. So again, the primary thrust behind this is to cut down on repetitive boilerplate and allow you to write more concise methods within object literals. You can also see on this slide that I've used template literals and a new API method, number.isFinite, in ESNext. So it's a mix of syntax that's still relatively familiar, but that makes it even easier to write tighter code. The next feature is probably one of my favorites, destructuring assignment. In sum, it allows you to extract values from arrays and objects using a syntax that mirrors their construction. Another intriguing use case for it is swapping variables without the use of an additional transient temporary variable. So here are some simple examples. In the first step, I'm importing the parse and stringify properties of the JSON object. In the second step, I'm executing a regular expression over, in this case, a phone number, and then assigning the area code and local properties. Now, when you run the exec method on a string, it returns everything after the first array element contains the matching capturing groups. And you can see that in the phone number, in the phone number regex, I'm capturing the area code and then everything that follows, and then the local phone number. I'm not interested in the full match, which is the first element of the array. No problem. All I need to do is use the array elision syntax by simply appending a leading comma. And that match will automatically be excluded from the variable assignment. In the third example, I'm swapping variables, so you can see that there is no need for a temporary variable. And this last example seems rather odd, doesn't it? It looks like I'm doing a reverse less than or equal to operator. What this actually is ES6's new arrow function syntax. We'll talk a bit about more in a bit. But what this does is it takes a request object that contains a headers property, and you can see that I'm extracting that directly within the arguments, and then returning the headers as well. So it allows you to write very tight and concise code. But destructuring assignment is also useful because you can extract values from a complex structure in nothing more than a single statement. So this example might seem a bit overwhelming at first. So let's break it down even further. I have an array of poets objects that contains T.S. Eliot and Ezra Pound. Incidentally, two of my favorites. Each poet contains a name property, a string, and an array of works. Each work in turn has a title property and a date. So let's say that I'd like to print the date and author of Rhapsody on a Windy Night. So what I do is first pull out the name property of the author using destructuring assignment and assign it to the author variable. In this case, excuse me. In this case, I don't want to use the name property because I think it's a bit too vague. I'd like to use a more clear variable name, so I define it with author. Then you can see that that I'm going to extract assignment values from the works array. I'm not interested in the first element, which contains proofrock, but rather in the second one. And then you can see that I'm using the shorthand syntax that I just introduced you to pull out the title and date properties. So it looks just like a regular object or array definition would, except instead of using it as the right-hand side of the expression, where I'm assigning a value to a variable, I'm actually pulling individual values out of those objects and assigning them to 3 variables. And finally, I'm using the new template syntax to print out each variable. So title by author was published on .date. And then the result, the interpolated result is Rhapsody on a Windy Night by T.S. Eliot was published in 1917. So this makes it, so all of a sudden now, objects or arrays returned from different functions become a lot more meaningful. You can create those ad hoc packages of data with object and array literals and then return them from functions and then destructure them in a single expression. Very cool. Next up, I'd like to talk about 2 operators that I think are complements of one another, and that is the spread operator and the rest syntax for function parameters. First, let's talk about spread. Spread, like function.prototype.apply, allows you to expand an array of arguments, but without altering the context or the this binding of an invoked function. It also supports constructors, which is incredibly difficult to do now in code. You need to write your own wrapper that invokes the constructor and applies it to an object, and even then that doesn't quite work for native methods. So ES6 introduces a nice sugar for allowing you to do that automatically. It also provides a convenient syntax for merging arrays and array-like objects. If you ever used Ruby's asterisk or splat operator, this won't seem like news to you at all. And it allows you to convert any object with a length property into an array. So a common pattern that JavaScripters use today is to do array.prototype.slice.call, which gets to be redundant, which is an incredibly redundant and repetitive pattern. So with ES6, we now have a language operator to allow us to do that. Now conversely, rest parameters supplant the arguments object. Arguments is an interesting array-like object that's available to every function and that looks array-like and that has a length property and you can iterate over its indices. Sets up interesting semantics between the index of the argument and then the corresponding named parameter, if there is one. So ES6 gets rid of this confusing syntax. Remember, it's only additive, so arguments will still be around if you're using it, but it now provides you with a real array that you can access in your functions and to have them take a variable number of arguments. A rest parameter always returns an array even when those parameters are omitted. So let's say that you have a function that accepts a named parameter and then a set of rest parameters, and you just invoke that function without giving it any arguments. Well, the named parameter will be undefined, as the semantics of language currently are, but the rest parameter will be an array, not null, not undefined, not some other unexpected value. So it saves you from having to implement additional defensive programming in order to work around that edge case. In short, this feature of language works to help you write cleaner code. So let's put this all together in an example that extracts the basic authentication header from a request object. In this case, you can assume that request is something like what Node.js returns. So I have a getCredentials function that immediately destructures the authorization property from the request. I then split it on space and then check the values. For basic authentication, you need to have the string basic followed by a space and then followed by the base64 encoded version of the credentials. Those are implementation details at this point. But what's important is that you can see that I can write the syntax, I can write this function in a much cleaner way with the new ES6 syntax. You can also see that I'm using the new string.prototype.contains method instead of doing .index of greater than -1. And finally, for the last result, once I'm sure that the header is syntactically valid, I extract the name and password by running a regular expression on it, discarding the unimportant full match, and then returning that in an object containing name and password properties. So this function would take about a third more lines of code and a lot more temporary variables to write in ES5 and ES3. So with ES6, I can cut down on cruft while writing more expressive code that allow me to effectively say what I mean. The next feature I'd like to cover is full Unicode string support. Now this is an interesting topic. The front-end web developer Matthias Beinens has done extensive research with encoding in JavaScript. So I've linked you to a blog post, and I post the slides later. You can You can really check out his blog post for a more in-depth discussion. But suffice it to say that regular expressions, the char@, charcode@, string.slice, and other string methods operate on code units, not characters. Now, in most cases, this doesn't make too much of a difference unless you're working with characters outside the Unicode basic multilingual plane. I believe there are something like 16 different, 16 planes. The initial basic multilingual plane and then astral planes following up. For characters in the astral planes, you need to represent them as surrogate pairs that actually comprise 2 code units, even if they appear as 1 character. So this introduces some interesting semantics where a string that looks like it contains only 1 character has a length of 2. If you try to retrieve the character code at the initial character, you'll see that it returns the character code for one of the 2 surrogate pairs. And you can see that string.from from char code suffers from the same limitation. If I then try to feed that character into string.from char code, I get back a symbol that's completely different from the one I started with. And you can also see in the last example that that character actually comprises 2 escape sequences representing the 2 surrogate pairs. So ES6 introduces a nicer syntactic convenience for this. It fixes regular expressions with the U flag that allows you to effectively use those. It adds the code point at and string.from code point methods that actually operate against Unicode characters rather than individual code units. And it also introduces a variable length Unicode escape sequence syntax. We can't fix length, unfortunately, because we do have to remain backward compatible, but it's still an important fix, especially when you're not always expecting input to be in the basic multilingual plane. Emoji comes to mind as a good example. Next up, I'd like to talk about 3 new data structures in EcmaScript 6, maps, WeakMaps, and sets. We'll start off with maps because they're a bit easier to understand. The primary purpose of a map is that they support sublinear lookup times. Finally putting JavaScript on parity with other languages that have long had hashes and dictionaries. Every map has the methods. So you have the standard methods as you'd expect. You can get keys, set values, check if a key is contained within the map, delete keys, clear the map entirely, or iterate over its keys. Entries are enumerated in insertion order. Interestingly enough, the insertion order for enumerating over regular JavaScript object literals continues to be implementation dependent. So maps finally define a predictable enumeration order. Weak maps use weak references to allow for garbage collection. We'll talk about that more in a second. And then sets can find unique array elements in linear time. So they inherit the characteristics of maps in that they must be unique, but also arrays, in which case you don't have a key value association, but rather a single value that you can store within that array. So I mentioned WeakMaps earlier, and we can go ahead and use this an example to build an element storage engine, something similar to how jQuery.data does it, or prototypes store, unstore, and retrieve methods. Now, the important case of WeakMap, in order to understand WeakMaps, it helps to know a bit about garbage collection semantics. I won't go into the full details of them, but suffice it to say that whenever you append a property to an object, that property maintains a strongly held reference, which means that until that reference is cleared up, the garbage collector can't touch it. Let's say that a developer wants to store a particular object in an array or in an object literal, and then return to it at a later date. If the garbage collector ran before they had somewhere in between there, they would lose access to that property, and it might even trigger a segmentation fault. So a weak map holds references weakly to objects, which means that if an object is no longer referenced by any other aspect of the program and only remains within the weak map, the weak map makes it available for garbage collection. So this is particularly useful in an element store. Let's say that you associate some metadata with an element, and then a few hundred lines later in code, perhaps you're writing a client-side single-page app, you want to destroy that element. You have no more use for it. So you call remove child on it, and you remove all references to it with variables. So sounds good, right? You've cleaned up all references to it. No, not quite. There is one more reference that's floating around to it, and that is in and that's in the storage map itself. And if you're using a map or an object literal, until that object literal is cleared, then that element would continue to sit and take up memory until the tab or the browser was closed. With a weak map, as soon as the last reference to that element is removed, it's safely made available for garbage collection. So WeakMaps implement the same API as maps do, with one important exception. You can't enumerate over their keys or values. Just as I said earlier, because WeakMaps are so heavily tied to garbage collection semantics, that means that one moment you might iterate over your map, and then it might have 6 keys in it. The next moment it might have none, because all those variables, all those extra reference to them were cleaned up and the garbage collector has run. So it exposes you to leaky implementation details. So for consistency though, WeakMaps are an incredibly powerful tool that allow you to store objects in a leak-free manner. The next feature I'd like to talk about are tag template literals. Now I used the template literal syntax in previous slides. You can see that they're escaped with backticks and that they use the curly brace syntax for string interpolation. Tag template literals allow you to specify a handler function at the very beginning of that string before the first opening backtick that allow you to perform additional pre-processing on that element. Now a handler function accepts a variable number of arguments. The first one is an array of raw values, the values that occur between the interpolations, followed by a variable number of arguments containing the substitutions. In this case, I'm defining a handler for escaping its strings for use in HTML. And incidentally, I'm using a non-tagged template literal within the body of the escape function. So templates all the way down, hooray. In this particular case, you can assume that name is either pulled from a database or pulled from within the app, but from some source that the user doesn't control. For simplicity, I've just assigned it to a variable. Let's say that I'm an evildoer, and then instead of specifying my name, I also specify a script element to try to open up a cross-site scripting vulnerability. Fantastic. Except, thanks to the tag template literal, I can parse over every substitution and then escape the special HTML characters within it. So the result of that tag template literal contains the HTML escape sequences. The next feature I'd like to discuss are concise arrow functions. These are based on expression closures, which first appeared in Firefox 3.5. And you can see though that they're even more concise. Instead of having the function keyword and then the parentheses around the value, you can omit the parentheses for single parameter functions, and you don't need to specify the additional function keyword. So this allows you to, again, write concise, tight code. Blocks are also not required, but only for single value expressions. And this next example is a little bit hairy. So let's break it down step by step. You can see that I'm defining an identify function that is itself an arrow function. I need to provide empty parentheses because it doesn't accept any arguments, otherwise it would be a syntactic ambiguity. And then I have it return an object literal. Now this object literal is wrapped in parentheses again because of a similar syntactic ambiguity in the language where curly braces are used as to both delimit blocks and object literals. So if I wrap it in parentheses, it's correctly interpreted as an expression, specifically an object literal. This object literal has a toString property on it that defines an additional function. Now in this case, I am using the block syntax. So so I don't have the function of the implicit return that you saw earlier with the filter example. So in this case, I need to specifically include a return statement. But then as you can see, after I run this function, it returns an object that contains a toString property that returns the value kit. So when I interpolate them into the, oops, my apologies. One second. This doesn't seem to be my day with technical difficulties. Alrighty, thanks for being patient with me. So, as I was saying, that value gets coerced to a string within the template literal that then prints the value kit loves JavaScript, which of course I do. Finally, the important point to note is that arrow functions are not just a concise body. Their semantics are identical to bound functions, which means that they have a hard lexical this binding, so the value of this is preserved and cannot be modified later, even by call or apply. And it also means that they lack a prototype property and cannot be instantiated. If you try to instantiate an arrow function, it'll throw a type error. So just something to keep in mind that not only does the arrow function introduce a concise syntax, it also introduces new semantics that are otherwise equivalent to bound functions. In ES5, the way to create these was to use function.prototype.bind. But now we have a language level construct that allows us to do it. There are a lot of features that I didn't quite cover in this presentation. There are proxies, symbols for private names. Proxies are powerful tools that you can use to implement traps for objects and completely control how the object is handled by the language. There are iterators, modules, generators, and classes, which I mentioned earlier. There's a binary data API. There's discussion about creating new pattern matching syntax to complement destructuring. There are new reflection methods. In short, there's something for everyone in the language. And whether you prefer shorthand syntax or you're working on a library that provides basic tools, as in the case of tagged template literals, let's say that you provide a library that has a set of individual handlers that you can use. There are the new data structures with maps, WeakMaps, and sets. There are changes in modularity with classes and modules, which are currently under heavy discussion and are slated for inclusion in the draft of the specification. And there are additional core refinements and convenience API methods. So one more question to answer. When can you actually use any of these features? So Firefox has supported some of these features since version 2.0. In fact, many of the extensions that are now being formally standardized in the EcmaScript 6 specifications actually started out as Mozilla extensions to the language. So they've had a very significant role in helping move the language forward. You can also toggle the Enable Experimental JavaScript option in About Flags in Chrome and Chromium to test some of these features out. And finally, Yuri Zaitsev, also known as Kangax, has published an ES5 compat table and has now published a version specifically for ES6, which tests for the support of new syntax and new API methods available in ES6. I also highly recommend following ES Discuss on Twitter. This is a feed curated by Dominic DeNicola, which digests tweets from the ES Discuss mailing list, where most of the discussion about language implementation takes place. And finally, I recommend checking out a project called Continuum, written by JavaScript researcher Brandon Benvey. This actually provides a self-hosted ECMAScript 6 virtual machine using ECMAScript 3 and 5 semantics. So if you open this up in your browser, you can actually interact with a pure ES6 implementation and see how those methods and new syntax will be implemented and how you can so you can experiment away to your heart's content. There are also transpilers like Google's Tracer, which allow you to take ES6 code, or preliminary ES6 code rather, and convert it into the corresponding ES5 equivalent. So in short, ES6 is rapidly approaching. There are many new syntactic extensions, and there really is something for everyone in it. And even if none of these syntactical features covered in this slide appeal to you, chances are there is that one tweak or even major feature in the case of modules and classes which may appeal most to you. So I highly recommend investigating that, checking out Continuum, and staying up to date with the latest language developments. And so I know that was very quick. I do apologize for the technical difficulties as well. At this point, I'd like to turn it over to questions. Thank you.
In your destructuring nested objects, is there plans to support deeper traversal? So you were using in your examples just like one key, and then what if you wanted something deeply nested? Could you say like parent.child.
You definitely can. That was actually demoed in this right here. Yep. So you can nest and extract parameters from an arbitrary length.
No, so like for example, if I wanted like name.works.title, could I just get that immediately and assign it to like a title variable? So I'm pulling this out, like for example, from in Ember.js, if you do like get and set, you can arbitrarily go deep into.
Oh, I see, and not have to worry about whether those properties actually exist or not.
Yes, exactly. So you'll just do nothing or return null if you're getting.
There was a proposal that's inspired by CoffeeScript's existential operator.
Like
I think that's still in draft status at this point, though. I don't believe it's slated for formal inclusion in the spec.
Thank you.
Certainly. No questions? Ready. Oh, perfect.
Also on this slide, the bottom line var, and then that really long expression equals poets. What would be the variable name, or would there be? What would be the name of the variable created?
There are actually 3 variables that I'm creating. They're bolded: author, title, and date.
Okay, I understand.
That's the purpose of the destructuring assignment, is to extract multiple variables and then assign them in a single line.
Hi, you didn't mention TypeScript as an approach to target, ES6 features. So what are your thoughts on TypeScript?
I actually really like it. I'm not particularly keen on the static type system. I think type systems in general for me have always been something of a weak point. But I love the fact that it implements the new class syntax. And I think the TypeScript header definition files that you can use with existing libraries are particularly valuable in the case of tools. So if you're using something like Visual Studio and you want to have immediate code completion for your API, just drop in that file and then it'll intelligently know what the arguments are and the values. So I think TypeScript is incredibly helpful from that point. I hesitate to consider it a transpiler at this point because it implements a superset of the EcmaScript semantics, but I think it is definitely a fantastic alternative if you'd like to experiment that. And you want a syntax that's a bit closer to JavaScript than some of the other compile tool languages that are out there.
Thank you. Thank you.
Certainly. Alrighty. Well, thanks very much for allowing me to speak, and get ready for the next talk.